Last time we have already covered the recursions, right? I believe most of you guys have already participated in the lab, and in the lab they also give you one problem about the recursions, right? So recursions actually are sometimes it's slow, right? Sometimes it's slow when last time we checked. If we compare recursion version versus iterations, right, using for loops, we're able to compute the Fibonacci numbers. This version would be much faster than the recursive versions. So, but there's still some cases that we will require recursions, especially when the thinking process would be simpler, and we will use this example in here. But before that, we will talk about something that might improve the efficiency of recursive, which is called the tail recursive. So if the recursive call, right, factorial helper, this recursive call is the last line of your functions, then if this one is the last line of your function body, because this is the only one, so the compilers, right, they might do some optimizations. Right? Remember, it's might. They might not. They might do some optimizations that they don't need to keep track of what's happening inside your functions, and they can do some optimizations. So the performance will be improved a lot. Right? As you can see, there's a slight difference between this version to compute factorial versus our initial version to compute factorial. In this version, we will use this fact to keep track of the current version, current output. Right? You can think of the partial output of your of the final output. But yeah. Anyway, you can read this code. And this one is called tail recursive. Put your recursive call to the last line of the functions, then compilers can do optimizations for you. But you don't need to know the details because we haven't covered about the function calls that we will create some stack, heap, and so on. Right. So let's go to this one. Hanoi Tower, right? So I believe last time at the end of the lecture, I told you to go back and practice it, right? How many of you have solved this one on your own? No? How many of you solved this by referring to some other materials? Have tried this one? Played with it? No? All right. So what's the input? What's the output? The input is number of plates, right? 1, 2, 3, 4, 4 plates. And each time when you move, you can only move the smallest one, right? The smallest one, move it once. And you cannot plate larger ones on top of smaller ones. You have to maintain this order, right? Larger ones has to be in the bottom, and the smaller ones has to be on the top. So how can we move? Yeah, today, thanks for them, they have a whiteboard. I'm not sure if you guys can see. Let me do it this way. All right, so if I have this one, then use a different color like this. The same. All right. All right. If I have just the one plate, you guys see that? If I have just the one plate, let me call it. This is the place 1, place 2, place 3, right? If I only have one plate, how can I move it to 3? Directly move it, right? There's nothing wrong with moving. Right? So our input and output is like this. So if I input is number of plates, 1, right? If my input is 1, I should output 1, 2, 3. I directly move this plate from 1 to 3. What if I have 2 plates? What if I have 2 plates? What should be the output? 1 to 2, 1 to 2, 2 to 3, 1 to 3. Yes, 1 to 3. 1 to 2, 1 to 3, and 2 to 3. Right? So what we are basically doing is first moving this the smallest one into the second pair, then moving the larger one to the third one, then moving the smaller one to the third. So we can doing this on and on and on, right? So this will be our input, this will be our output. Our output is a sequence of instructions telling you how to move this plates. Right? So let's assume we have n plates. 1, 2, 3, 4, and so on, and putting. We are making the largest one special. How can we move it from 1? I can move it from 1 to 3. Right. So this is our question, right? We have generalized it to some questions. This color. So if we have n plates, right? We can think of the first part is n minus 1 plate. They are in order, right? And we can visualize this one as a smaller problem. So the basic idea is, okay, how about we move this n minus 1 plate to the second pair, right? This is step 1. Step 1, we in our initial state. Yeah, I should put step 1 in the middle. Step 1, move n minus 1 plate to the middle, right? N minus 1 to the middle. So the basic idea of recursion is don't care about how they move it from one place to another place, right? We just assume our functions can do that because it's a smaller problem, right? If we are trying to solve the problem for n plates, we assume we already have the version for n minus 1 plate. So if we already know how to move n minus 1 plate to the middle, then our next step, step 2, right? We'll move this plate to that place. So it will be empty, still this n minus 1 plate, and the last one has this plate, right? And our last step will be move this n minus 1 plate to the third pair, right? So we are done. So that's the basic idea of this handling power. Any questions on this basic concept?
Top plate is n minus 1.
Pardon?
The top plate is n minus 1.
Yeah. So assuming the total is n, so this one is n minus 1 plate, right? If we already know how to solve n minus 1 plate, moving from one place to another place, we will keep the bottom one untouched, right? It will remain there. So let's see. So any questions on this one? This concept? Conceptually, this should work, right? We are trying to moving n plates from one place to another place. So let's see typically how we can code that. So let me create another file. what we are trying to call is, for example, we can see in a number of plate n, right? And then we can see in ask a user to give us the number of plates. Is it? Then we can call this function n. Right. This is something we are trying to call, and we have to implement this function. So as we have defined, our function should accept the number of plates, right? Number of plates. And inside here, we said in this one, we should move and plates minus 1 plates, right? We should then move, in this move, we just see out from 1, 2, 3. Let's first use the simplest version. It won't work, but we will make it work. Right. This is our basic idea, right? First move n minus 1 plates. Then we said, okay, we want to move the last plate, right, from 1 to 3. Then we will print out we will move the remaining n minus 1 to the right place. So what we are missing is, as you can see, this line number 5 and the line number 7 are exactly the same, but they shouldn't be the same, right? Their starting position and the ending position should be different. So we should give them some positions, like this one should be starting from 1 to 2, right? This one should starting from 2 to 3, right? We should do something like this. Right? We are trying to move n minus 1 plates from the starting location to the ending location. And similar here, we are moving, after we move 1 to 3, the final step will be moving the n minus 1 plates from the second pair to the third pair, right? But as you can see, our Hanoi doesn't accept the number of locations, so we should make them as the start and end, right? Where is their starting location and where should we put into the end location? So in our function call, it should be different, right? We are trying to move from 1 to 3. But there's still some problem, right? What's the problem? So the problem is, initially, our function only works for moving from pair 1 to pair 3, right? We now need to support from arbitrary starting position to arbitrary end plate, right? So we cannot use this kind of hard-coded positions. So if my start position is n plates in here, so this n minus 1 plate should also starting from some starting position, right? We should move from starting position to some temporary position. Let's call it this one some temporary position. We haven't defined temp yet. Let's call this number a temp. And finally, when it is done, we need to move from the temp position to the end, right? And in here, we are no longer outputting like this. We are outputting start, arrow, our end, and a new line. Right. Here is our basic thinking process. So if we want to move n plates from start to end, we will have some temporary or some empty pairs, right, that don't have any plates. Then we can move n minus 1 to this temporary place. Then we can move the last plate from the start to end, and then we can move n minus 1 plate from this temporal position to the end. In this case, right, we will move this temp equals to 2, right? This is the temporary starting position is 1, ending position is 3, temp position is 2. So we are trying to move n minus 1 from 1 to 2, right? N minus 1 plate from 1 to 2. Then we are moving the last plate from 1 to 3, moving the last plate from 1 to 3. Then we are moving n minus 1 plate from this temporary position to the end. Any questions on this? We're almost done. Yeah, here is moving the last plate. See out, start to end. We use this one. Yeah, we just printing out the sequence. You can also store it in some place, but we just simply print it out. This start to end, which is moving the last plate. This last plate. Any questions? All right, so we have the remaining questions, right? How to compute temp? How to compute temp? There are basically two ways. One is you can remember where temp is when you are getting inside, or you can compute it on the fly, right? Because we know there's only 3 plates. Right? It's a bad design. I will just simplify this code. I will mention that bad design would be something like 6 minus start minus end, right? If they start, because we know start position plus end position plus temp position equals to 6. 1 plus 2 plus 3 equals to 6, right? So the temporary pair should be 6 minus start minus end. But it's a bad decision because it can only support for 3 pairs. Anyway, let it be this way because it will be much easier to read. All right. Let's first try to run it. What's this called? And one. Yeah, wait. We haven't defined the special case, right? What if there's only one plate? We haven't defined the special case. Let me put a special case here. If number of plates equals to 1, what should we do? This one is easy, right? We just see out. Wait, we just see out the start. Yeah, it will be exactly the same as this one. So I just copy it here. Is it correct? If there's only one plate, we directly says move from start to end. Right. This will be the special case. So let me recompile it. And then let me run it. If I import it as 2, oh, segment touching for. Let me see what's wrong with it. If number of plates is these from 1 to 3, 1 plus 2, temporary. N minus 1 from 10 to end. 1 to 2. Let me try one. Still segmentation fault. So if my input is 1, I am calling 1 to 1 to 3. If number of plates equals to 1, I'm out, start, arrow, end. Why there's a segmentation fault? Oh, I didn't return. Sorry. Yeah, it should work. Working. All right. If my input is 2, right? If my input is 2, my output is first 1 to 2, then 1 to 3, then 2 to 3. Right? How about my input is 3? It is longer. 1 to 3, then 1 to 2, then 3 to 2, then 1 to 3. As you can see, for anything, right, you can split them into 2 parts. First, 3 operations. That is moving 2 plates. For example, if I have 3 plates, right, you can check this, the operations in the middle. This 1 to 3 is the separation, right? Separation from the first recursive call and then the next recursive call. The first recursive call contains 3 operations, 1 to 3, 1 to 2, 3 to 2. You can verify that these 3 operations will move 2 plates from position 1 to position 2, right? And the remaining 3 operations after 1 to 3, you are moving the 2 plates from position 2 to position 3, right? It's a recursive call, and you can also see from here, right? If there's only 2 plates, 1 to 3 is in the middle. It splits the total operations into 2 parts. First part, moving n-1 plate from 1 to 2. The operations after 1 to 3 is moving n-1 plate from 2 to 3, right? So that's something about the recursive calls. And you can continue try. How about 10? I don't know how long does it take. Oh, it's fast, right? It contains a long sequence of operations, and you can do that, right? It's not that hard, right?
How did you get 10?
Yeah. So here is some trick, right? This is the intermediate pairs that's empty. If my input is 1 and 2, the intermediate template, the intermediate place should be 3, right? So basically, I know their names are 1, 2, 3, right? I know their total will be 6. If you already give me 2 positions, this temp will be the 3rd position. There will be some other way people typically like to use is like this. They would like to put 2 here, and they call it. Let me put temp here, just using the same name so that you won't be confused. So typically, what we do is comment this out. All right, so what does it mean? It means in this function, right, I'm trying to move n plates from 1 to 3, and there will be some empty position called 2, or some intermediate place called 2. You can use that. So in this function, what you can do is, okay, how about I move n-1 plate from the start to the temporary or the intermediate place through some other intermediate place. Now your intermediate place is n. Right? You're trying to move from start to n, but you can use some of the other place, which is called n. Similarly, in here, you're trying to move from 10 to the end, and you can use something as the intermediate place for the start. So there's another way you can write. Right. This would be the typical way people trying to write. You can remember the tempo positions. Any more questions?
Yeah. Number 6.
Number 6, I just noticed there are positions, right? Positions 1, position 2, position 3. The total will be 6. Because I know start plus end plus 10 will always become 6. Right? You are moving from 1 to 3 through 2. So 1 plus 2 plus 3 equals to 6. If I only give you 1 and 3, you will know the intermediate place will be 2. You can directly compute that by 6 minus start minus end. Any more questions? So this would be a perfect place that can train your recursive thinking, right? So after last lecture, students will still come to me and ask me, okay, what if, right? If my input is 10, then I need to go in here to see what's happening when the number of plates equal to 6. When they are dividing into number equal to 6, they are trying to figure out what's happening when number of plates equals to 8. Right? You need to go on and on and on. You cannot basically when the number becomes large, you cannot iterate all this process. So the basic operation or the basic thinking process of recursive design is assuming it happens, assuming it works. Right? Assuming it works for n-1 plate, they can successfully moving n-1 plate from start to 10. What you can do, right? If they can successfully move n-1 plate from start to 10, then we can move it first, then moving the last plate from start to end, then moving the n-1 plate, which now is in the 10th position, right? And move it to the end. We need to make this kind of assumptions. Whenever we design a function, do not doubt it. Right? We simply assume it can work successfully. So these are some places that recursive thinking will be much simpler than iterative. Right? If you need write a for loop to do it, it will be a nightmare. You guys can try it and convert it into a for loop. It's very hard. All right. Any questions? No? Okay, let's come back. So this is the well-known puzzle, and it can be easily solved using recursions. And there's one more thing is about, again, I need to emphasize readability again. Right? If you are trying to convert this solution into iterative one, your code will be very hard to read. Other people will not be able to understand it, most likely. But if you are writing in the recursive way, it's very easy to read, right? You can directly read it when someone else gives you this code. Okay, I'm moving n-1 from one place to another place. Of course, you need some comments. For example, you need some explanations in here, right? You need to tell the reader what handling does. Right? You can simply say it is moving n plates from start to end, right? And after you have this, these comments, people will be able to understand when they read the code. So it's more about the readabilities. Readability is very important. And when you write it in a recursive way, these solutions will be very easy to read and very easy to understand. All right, so another exercise will be merge sort. It's actually quite hard, right? If you need to keep track of the index What does merge sort means? If I need to sort an array, right? Yeah, the area I have board, I like to use board. If I have an array or a factor of numbers, right? 1, 3, 2. I want you to sort it into, let me give it one more number, 4. I want it to become 1, 2, 3, 4. Right? This is something we are trying to call sorting. We are making them the ascending order or descending order. So what does merge sort mean? If I have 1, 3, 2, 4, right? This is my input. A factor of arrays, a factor of int. A factor of int, right? I'm trying to sort it. What can we do? We can sort the first half, right? Getting the index, making them 2 parts. So we can create a factor called the left, a factor called the right. Right? Then we can sort left, sort right. That's what we call means a merge sort the first part, merge sort the second part. Right? This one, let's call it the left. It's again a factor of input int. And the right part, similarly. Right? What are our assumptions? Our assumptions is sort can successfully work when you are doing sorting. So what is the sort of left? Sort of left becomes 1 and 3. Sort of the right becomes 2 and 4, right? We are assuming they can successfully work. Then how can we merge them together? We can have some index, right? Looking at them one by one, which one is smaller? One is smaller, then our first element is 1. Then we go to the next element. We compare 2 and 3. 2 is smaller, so next one is 2. Then we move this index to the next one. Then 3 and 4, which one is small? 3. Then remaining is 4. Right? This is basic ideas about sorting the first half, sorting the second half. Then we can merge them. And maybe in next semester, when you learn algorithms, you will know this kind of sorting will be much faster than bubble sorting and some insertion sorting and so on. So this one is the efficient one. Any questions on it? I just want you to know the basic ideas. You want the code, you can ask ChatGPT. You can ask, run me a C++ code about merge sorting. You can quickly write it down the code. It's so common that the code are everywhere, so you can check online. All right, so the basic idea is still recursion. So recursion are everywhere almost. So we are almost done with the recursions. We need to look at another problem. It's called the variables scope. So when you define a variable, right? What are a variable? In this one, end plate is a variable, right? Start is a variable. This number n is a variable. And also, if I define temp here, temp is another variable, right? So what are the scope of a variable? And also, who can see which variable? Like if I am in main function, can I see the temp variable in main? If I am in the Hanoi function, can I see what's the value of n? Right, that's the problems. That's called the scope. And you can have variables with the same name in different functions. It's actually true when we are calling a recursive calls, right? We will have the same name for different functions. And the the part within a program in where the variables are visible is called the scope, right? Outside of the scope, they cannot see it. And let me see if we have more, right? We have typically two types of variable scopes. One is called local, one is called global. So global variables are seen by everyone, like the see in. This one, see in, see out. They are global variables. See out, see in. They are still variable. They are global variables. Everyone can use it, right? It's inside everyone's scope. But some of the variables are local, such as this n. This int n is local to this main function. And this 10 is local to this function block. No one outside can access it, right? If you want to inside the main function, you can check the value of 10. You cannot do that. It doesn't exist. And similarly, in Hanoi, if you want to check the value of n, you cannot do that because it's outside of your scope. So that's called the scope of a variable. And this variable, the scope are defined by the braces, right? Simply by the braces. Inside every brace, it's a new scope or a new block. Let's look at some examples right in here. This function called is a scope. It has many variables. Variable r, variable initial balance, p, and n. No one outside of this function can access these values. They are local to this function. It's local variable. And also inside of the main function, right? You have one brace, two brace. And we intentionally make the life harder. How about we define a variable inside of this brace? It's still inside of the main function, but we define it inside another brace. We create a new block and define our variables here. That's called R. And we see in R, the question is, can someone outside of this block access R? I'm trying to access R, but it's outside of the brace. And the function called use value R. Right, that's the question. Is R visible outside of this block, this small block? Yeah, the answer is no, because this is your scope. Everyone inside it can see R, but everyone outside cannot see it. Yeah, so that's the definition of a scope. No questions? I saw someone discussing, but anyway, let's move on. So global variables are variables that are defined outside of functions, outside of your main function, outside of any of your functions, right? And it's visible to all functions that are defined after it. But we will not mix this one with some of the visibilities when we're defining multiple files. But anyway, let's assume that we only have one file. When you define a global variable, it's visible to all these functions that are defined after it. So that's called a global. And some of the global variables you cannot be avoided, right? Like see in, see out. You have to make them global so that when you are trying to print it, you can directly use it. And the basic rule is try your best to avoid global variables. Right? Try your best to avoid that. And we will see how we can avoid that, right? We can put variables inside functions, inside this kind of blocks, or we can put some of the variables inside a class. We will talk about that later. So these are it's more of a style issues, right? We can still define global variables, right? Your program can work, can run, but it's a bad style. So this one, and as you can see, we can define a balance here. It's a global variable, and we can use this. We can directly modify or use this balance in our future value function. right? You can use these balance. And also the balance can also be used inside in the main function, but we can still continue to use it. And right. So sometimes you will feel this one is very convenient, right? You don't need to make balance as a parameter in your function. So in the old ways, you need to put it as a parameter in your function. But now you can just define many global variables, and everyone can modify them, and everyone can see them, everyone can print them. So that's convenient, but it's better style. Right? Try your best to avoid global variables. All right, so another one is, what if they have the same name? Right? Global here, global here. What if they have the same name? What's the output? 1, right? Yeah. The answer is 1. We have 1 global, 2 global, and inside this block, because we have 1 global, so we will look at the innermost one. If we didn't find the global, like the previous one, right? If in our function, we first check if there any variable called balance defined in this block. If yes, we directly use that balance. If no, we look outside of our block, right? Look at this one. If there any variable defined with the name balance, yes, then we use it. So if they have the same name, always use the innermost one, right? And when you have more and more nested blocks, we will look outside one layer by one layer until we find a name that matches this one, this variable name. One thing that's different is called the lifetime, right? So in here, for example, in this function, we have local variable called p and n. When this function call ends, p and n will be destroyed. That's called the lifetime. So whenever this function call ends, p and n doesn't exist, even though they are local variables. If you look at here, the lifetime, right? As you can see, this smaller factorial. If it's outside of this braces, outside of the block, they doesn't exist. That's their lifetime. One thing different is called static, right? Static. The question is, how can we count how many times a function is called? Yeah, you can define a static variable for the count. Let it keep track of how many times this Fibonacci function is called. Right? You don't know how many times this one is called because you have so many recursive calls, right? Sometimes you will lose track of that, but this count will help you keep track of that. This static means it will exist even if this function ends. Even if this function ends, this count still exists. But remember, there's still some scope issues, right? Scope of count is still within this block. So no one outside of your function can access count. That's called scope or visibility. Who can see your variable? Who can see your variable? But the lifetime is different. Lifetime, the count, lifetime is until, for example, the end of your program. Whenever your function call ends, count still exists. And for different variable, for example, this f, whenever this function call ends, this f will be destroyed. Whenever this function call enters, we will create a new version of f. Right? By this count, we will have only one version. And if you just look at this program, what's the problem? Is this count, will this count output as expected? If you look at n equals to 3, right? count equals to 1 because each time I increment by 1, right? Second time this function is called, I would output fib is called second time, right? 2 times. When the third time it comes, it will output fib is called 3 times. Is it output as expected?
From the previous.
Not exactly, actually. It's more complex than that. So let's look at what will happen. All right, this is our function. Let me clear this part. I believe I have already tested that. Right? Maybe 10 is too large. Let me make it a smaller one. Let it be 3. Okay, so some weird things happening, right? Fib is called 2 times, fib is called 3 times, fib is called 3 times. Yeah. That is because when you are executing line 9, in line 9, when you are calling fib n-1, it will change your count. When you call fib n-2, it will change your count. So after you execute line 9, you are trying to execute line 10, this count is already modified by some other function calls because they are referring to the same count each time. We can check that with our debugging tools. Right, let me use these debugging tools to show you. Let's see, is it good to break in here or break in here? Anyway, let it run. Let it run for a few times. Is it done? Oh, it's only 3. Let me create a larger one. 10. All right, I press it 4 times. And maybe the more important thing is the call stack. Wait, can I push it up? No. All right. I'm not sure if you guys can see it. So in this call stack, right, in our main function calls fib once, calls fib twice, calls fib 3 times, calls fib 4 times. We haven't reached the line 10 yet of the outer function call. And as you can see, there are local variables called count equals to 4 for this function call. And let's check out the previous function call. This is the previous function call, and also equals to 4, the previous call, and equals to 4, the previous call, and equals count equals to 4, right? So when we enter, the n equals to 10. But when the first time when we call this one, the count should be just 1, right? But after we call it a few times, this count becomes 4. And the next time, when we keep running, count becomes 5, right? So this count, because it's a static, there's only one version for it, for this fib function. Whenever you call fib, it is incremented. Whenever you call fib, it is incremented. So if you see out in here, it will be wrong. All right. And for other variables, right? Other variables like the int n, this n and this f. Let's look at f. F is again a local variable, but the lifetime is only for this function, right? And each time when you call this function, a new f will be created. If we check the call stack, right? This is the initial version. This is another version. This is another version. This is another version. This is another version. All of them have different f's, right? If you look at this f, from n equal to 10, some weird number, n equal to 9, weird number, n equal to 8, weird number, right? 7, 6. All these f and n, they are local to this function. Their lifetime are exactly the same as their scope. So whenever a function calls, a new function created. Whenever a function ends, the variable will be destroyed. And as you can see, they can have different names. They can have the same name, right? All of them called f in different function calls. All of them are the same. So these are the difference between this called lifetime. Any questions on that? The static. The only tricky thing is the static, right? If we want to make this variable exist even after this function ends. No? All right. So how can we fix it? How can we make this C out correct? How can we make it correct? We want to say fig is called 1 time, 2 time, 3 time, 4 time. Put it in a if statement. Inside of this if statement. Is that what you are referring to? If we put it here, what will happen? We mean something like this. What will be the output? By simply reading the code, what's the output? Let me put a 4 here so that we can, let me put a 3 here so that we can see the output. I shouldn't use it in the breaks. 2 times, 3 times, right? If I put a 4 here, 3 times, 4 times, 5 times. How about we put it before here? What will be the output? 1 time, 2 times, 3 times, 4 times, 5 times, right? We should put it before this if else statement. Right, this is the quick fix. All right, let me close it. This one will be actually harder. It's still recursion, but we will introduce a new thing called backtracking. So it's like you are putting n queens. So the queens are for the chess, right? Queens can eat anything, the same row, the same column, and also the same diagonals. So you cannot put queens in the same row, put queens in the same column. You also cannot put queens in the same diagonal. So this is called n queens problem. If I give you n queens, how can you put these queens in this board? What will be the output? Output could be just the locations, right? This one can be 0, 1. This one can be 1 and 4, 1 and 3. This one will be 2 and 0. Right? It can be the index, or you can output the whole board. All the others just a dot. Here you put a Q. Other places a dot. You can output something like this.
Any one possible
Yeah, any one possible solution would be fine. Yeah. So, right. So your question is output what kind of solutions? There will be many solutions for this one. And yeah, so let's look at online version. Actually, I can code it by myself, but the time is limited. I just show you the code. Here's this website. Let me hide it. Geeks for Geeks. All right, this contains many of these solutions for that, and you can check in the left side, right, how to print all of the solutions, how can print one, and so on. You can go to some of the tutorials to learn more. So this is a good place that you can learn coding. So what's the typical thinking process is like this, right? Initially, you have an empty board. Assuming you will start with the first column. In the first column, you have many choices. The first choice will be put in the first location. Second choice will be put in the second location. Third choice will be put in the third location, and then fourth location. Right? You can try all of them. And for one of them, you can continue to try the second column, right? Because no queens can put it in the same column. You can try the second column. If I put it in the first place, no, because they will eat each other. How about second location? Because queens can eat the diagonal. No. Then how about the third location? It works. It works. Let me iterate all the possible solutions. Right? Third location, fourth location. These two, we can skip them. And for this one, we continue about putting the queens in the third row, on first place, second place, third place, fourth place. Right? All these solutions will not work. Right? If I put it in the first place, it will be eaten by the first queen. If I put it in the second place, it will be eaten by the second queen. Third place, eaten by the second queen. Fourth place, eaten by the second queen. So all of them will be wrong. Then we can come back and so this one cannot work. Then we move on to this and try all these possibilities. So here are the basic process, right? So how can we convert it into some code? It's like, let me see, right. Here is a simple one, just to print these solutions. And let me continue. They also have a function called isSave. If I give you what kind of solutions, you need to tell me true or false. Is it possible? Is it safe? And no queens are eaten by any queens, right? This is the function. We can check any of them on the same row, any of them on the same column, any of them on the diagonals, right? These are the basic functions, but we will skip this one. This one is just to check if one kind of positions are possible. Let's look at the main one. If I want to solve n queen problems, right? First one, let me see in here, right? There will be n positions for the current column. Right? We are putting queens column by column. For the current column, we will try all possible solutions for I, which is the I equal to 0 until n minus 1. Right? We will try them one by one. I is the row. The column is a fixed number whenever inside a recursive call. Right? In some other recursive, so if this one is safe, we can put it in this position. Then we can continue to recursive call the next column, right? The same function, solve n q utility, is the same recursive function, the board, and we will check the next column. We will put queens column by column. And as we can see, if any of the solutions for the remaining solutions are true, we are done. Right? Because it's a recursive call. Recursive call means if column plus 1 is done, inside column plus 1, it will check column plus 2. Inside column plus 2, it will check column plus 3. Right? If all of them return true, it means you are done. You are done with placing these queens. So this one. And what if it fails? here comes the backtracing. Backtracking is if this one fails, it means you cannot put current queen in this ith location, right? You have to mark it back to no queens. So here is the one, right? Let me explain again. First, if this position is safe, we can put a queen in the I row and this column. We put the queen, then we will check if I put the queen in the current position, will it give me the correct solutions? If yes, we are done. If no, means we cannot put our queen in here, right? Then we will mark it back to 0. What we will do is similar to this one, right? When our recursive call comes here, we will check, is I equal to 2, which is this position, right? If I put a queen in here, it's safe, right? We still check, is it safe? Is it safe? False. Is it safe? False. Is it safe? True. If it's safe, we will try all the possible solutions after me. If any of them becomes true, it's true. If all of them becomes false, it's false, which means I cannot put a queen in here. But in this loop, I have marked, I have put a queen in here. So I need to undo it, right? I need to undo it. It becomes empty. Then I can keep adding queens in here. Right. So yeah, this is the basic process of backtracking. Whenever one step is wrong, we undo it and then keep trying the remaining solutions. Similarly, because all of them are false, I know the position shouldn't be in the left up corner, right? I will undo it and put the queen in here. And then we can keep tracking, right? As long as any of the solutions are correct, I will return step by step and return it to here, true, return to here, true, return to here, true, return it. Right. So this is called a backtracking. So any questions on it? After you get it back, you can click on the link and following the linking process and all these steps, especially with 4x4, it's easy to debug it, right? You can keep track of all the process, what they are doing inside of their code. Their code are, this is the main part, right? These 3 lines are the main part. Try this position, solve the remainings. If didn't solve, undo this current position. This is called a backtrack. All right, if there's no more questions, I don't have any more in here, so we will go to the class. All right. So this one will be much easier than recursions. So struct and the class, the goal is to implement your own class. A class is like a type. You are defining a new type. Instead of just the basic types like integer, double, strings, characters, right? You are trying to define your own type. And you need to understand what is called such as the declaration versus implementations. And you need to understand how an object is constructed. So after this class, you will have the basic understanding of the object-oriented program, which is called OOP. So the first, we will start with something that we have already known, right? We have a bunch of variables, such as we have talked about, for example, computer products, right? We can have a name. What's the name of your computer, or what's the brand? And also, what's the price? What's the score, right? How can you group this kind of related information together? That's the starting point of the learning structure or class. Some of the code, for example, if everything is independent, right? We can have some score, we can have some price, we can have best score, we can have best price. We want to find out which computer should we buy. Now we will compare if we divide the score versus price, compared with the current best one, right? If the ratio is better than the current best one, we will keep track of the current best one as the new one, right? If the next score versus divided by next price is greater than current best, then we say the best name as the new name, the best score as the new score, and the best price as the new price. But these kind of ways these variables, they are quite distinct, right? When you're trying to read or understand what other people are doing, this kind of code are not that obvious. So here is some code other people might write, right? Have some of the variables, seeing the next name, price, and the score. Then if it's better, we will always, the key idea is finding out the best product, right? So this will be a one. So how can we modularize it? We will, for example, implement some functions called is better than the best, right? We can create a function called is better than the next, and then we will have a bunch of parameters, right? Like the next score, next price, best score, and best price. And we can put it in here. If the next score is better than the current best, what we will do. So instead of doing that way, right? Every variables are independent. We can group them into some structures, right? This is called C++ structures, and it also supports. It also works in the C version. The old C, they support the struct, so that different components can be grouped together, right? All of them will become some properties of your product, right? If you have a computer product, it has the property name, it has a property price, it has the property score. And this struct is a keyword. It means you cannot use some variable name called a struct. It's a keyword. It's a reserved by the C++ language. And the best practice is the first letter of the struct or class should be a uppercase, and all the variables are lowercase. The product, the class name or struct name should be capital, right? So it's just a style issues. When you write it this way, everybody will agree. And for these ones, they know they are simple variables. This one are this struct names. You use a capitalize it, the first one, right? And we call each variable, the name, price, score, the member of this structure. And don't forget the semicolon after this brace, after you define this structure. And until here, you are actually defining a new type. The type is called product. Right? It is exactly the same as integer double. So you can create a vector of product, right? An array of product. You can use product as anything that will become a type. And you can define variables, or we call it object. If we have a class or struct, then we can create, you can think of this product as some type, right? Like integer, int. You can have two variables, right? Similar here. If your type is product, you can have two objects. So what's the difference between a class and an object? First of all, class is a type, right? It's a virtual idea. For example, you can define what is a human, right? Human has a body, has head, can move, can eat, and so on. But when you are talking about the specific people, right, like me, I am one kind of human, for example, then I am the real object. So the product, the type definition, it doesn't consume any space in the computer. But whenever you define a product, it will consume some space inside your computers. All right. So let's continue. And we can access the members, right? Like name, using this one, such as best product dot name. We can access these members using this way, and we can assign them, right? Best product dot name, assign it as other people's name. And all these types inside here, strings, double int, they can also be another struct or class. Also fine. They are just some types. Here is the example of rewriting the previous one. Right? We can define a structure. This is we can group them together. Remember, here is the type definition. It's only a type. We haven't defined any object yet. And in here, we can define an object, right? Product of your next product. You can see in the next product's properties, and we can compare this one, these two, and we can assign these members, right? Name, score, price. We can assign a new value to it. And what's the benefit of doing it is, if you can modularize it, modularize the original one, it becomes a one that's better to understand, right? This is better than best. We'll accept two products, like next product and the best product. You kind of know what this function is doing by reading this head, right? It's simply comparing two products. Versus the initial one, we have name, we have score, we have price, and so on. But in here, whenever you use the product, it's easier to understand. It will help you have better readabilities. It's a very good programming style. Okay, I think it's time for a 15 minutes break. All right.
那个 count 那里我还是有点搞不懂，
那个这个
243，对对对。
对，因为是这样子，就是我看一下，let's change things 就是这个嘛，因为它是一个 static 的 type，说明它会一直存在。你每一次 call fib 的时候，它都会存在。本身的 version 是这个样子啊。本身是写在这里，对吧？那么你在运行开始 n 进来，比如说是4进来啊，4进来以后，我先运行第12行，我先调用了 fib 3和 fib 2，在我 output 之前，我已经在调用别人，在调用这个的时候，他们会改变这个 count。调用 fib 3，它会改变 count；调用 fib 2，它又会改变 count。
不是一进来就 count 加1了？
对，就是一开始是0嘛，对吧？fib 4进来的时候 count 变成了1。但是它在运行12行的时候，它调用 fib 3的时候，对 ，kit 变成了count 变成了2。对。后来又调用在 fib 3的时候，它又调用 fib 2，它又把 count 加1，它变成了3。对，这样就一次一次你就搞不清楚它的 count 到底是多少。对，你可以用那个 VS Code 来 debug 一下。对，但是它这里的输出，因为在第12行之后。所以它的 count 其实不是它这个1这个 count， 它是后面的 count。
但是就是把 fib 3全都操作完了，它才
对，它才输出。是的，对。
那为什么会有2次？对，3 times。
是这样子，就是它最后还是返回了嘛，对吧？一开始是我的输入是多少？我的输入是3，对吧？3的时候3进去，count 先变成了1，对吧？然后3进去以后，它进入了一个 fib 的2和 fib 的1，然后 fib 的2的时候，它 count 变成了2。对吧？然后它因为它小于等于2了，所以它这个 else 不进，那么它第一次输出就是2。然后它又跳回来，跳到它的父辈那里，它又调用了一次 fib 的2，应该
就是1吧？
你在 fib 3的时候，等一下 ，fib 4的时候调用了 fib 3和 fib 2嘛？刚刚运行的是 fib 3的那段，现在开始调用 fib 2了。fib 2的时候，
写的不是 fib 2，
那个是第一个 fib 3里的 fib 2。 对
哦，
对，它在 fib3的时候，它又调用了一次 fib2，对，就是在那里的时候的 fib2，但是这里后来出来又调用了一次 fib2，它的 count 就变成了3，对不对？然后在 fib2里面 count 等于3，那么它会输出 count 等于3，然后你又跳回复节点 fib 等于n等于4的时候，它又输出一遍3，对，就是这样的一个过程。
那我给他试一下，他应该输出是3445。
是吗？
是4的时候是吧？我刚刚讲的是3的时候，对，我刚刚讲的是3的时候，对，3的时候是输出233，对，是的，就你要慢慢的走进这个一步步调用的过程中才是，
他应该是3445。
对，是的。
它只有当 n 小于等于2的时候，它才会输出，不然它就会就是都会往下。
每个人都会输出，但是关键是 n 小于等于2的时候，它就会直接输出，别人的时候是调用完这个以后再输出，对，就这个区别。
就是既然全局变量这么好用，在其他都不用处理，为什么我们要尽量避免使用？
你现在写小程序没问题哈，一个代码里面，比如说就写那个 balance， 但是你程序一大了以后，你定了一个 balance， 别人定了一个 balance， 那个人又定了一个 balance， 这样你们就会相互之间冲突，它就会重复定义。
但是，重复定义如果在函数里面，它不是也用的是函数里面的定义？
不，如果别人也定义了一个 global 的叫做 balance， 那么你就会冲突，compiler就会报错。
它主要就是担心重复定义。
一个是重复定义，还有一个是别人不知道你这个到底是什么。C in C out 别人当然知道是什么，对不对？当你写个 balance， 但人家在引入你的包的时候 ，include 你的包的时候，他们就不知道你这个到底是在说些什么东西。
好的。应该就是这么说。
那我注意到，就是我上次在 lab 课上，就是就是如果我用到 vector 嵌套 vector 的形式，就是如果要用传参的话，它就是那个老师跟我说他会就是占用很大的内存。
对，你用 constant reference。
就只用 reference，
用 reference 就不会复制。然后你不想改变它就用 const。
但是就是他当时给我的方法也是设置全局变量
也可以，对，就是这个是比较差的一种方式，对，用 reference 或者你看这个它也是同样需要一个 board 的，对吧？它也同样需要一个 board， 它其实就是一个指针或者 reference 的意义，这就是一个指针或者 reference 的意义。
那如果我知道 Python 里面如果要用是在局部里面用全局变量，它会加个 global 的形式。假如说我局部和全局都有 balance 这个名，然后如果我想在一个函数里都用到，是不是也要用 global 的形式？
好像是有，但是我很少用，因为我很少定义全局变量。对，应该也有类似的功能，我猜是。
老师，那个 struct 我能不能用 struct 套 struct？
可以 ，struct 可以套 struct 里面可以套无穷多的东西。
就是也是嵌套式，然后就是一直点下去。
对，无穷套啊。可以。
好。老师，那我能不能理解成它 struct 就是 dictionary 类似的？
不一样。它跟dictionary 有什么区别哈 ？dictionary 加了一个哈希，对，它建立了一个，它为了让你快速搜到，它建立一个哈希表，然后让你可以快速的搜索到某一个东西。它跟 dictionary 还不太一样。
那我能在就是说实话 struct 之后后面再改变它吗？不可以
，struct 只是定义了一个新的类型而已。如果你要改变的话，就要定义一个新的类型。
就是我的意思是说，
就比如说你这个 product，你定义了一个新的类型，然后你要定一个新的，那就要建一个新的 struct。对，但是它的 object 是可以，这个类型是不行，但它的变量是可以。这个你可以变化它的大的内容。
这个能变内容，
对，
就是一直改变它的。
对，是的。
那你刚说哈希是什么？
哈希有一点点复杂，怎么说呢？就是它建立了一个
类似于搜索。
对，因为你大部分的匹配哈，它需要耗时很长，但是如果你用一个哈希表啊之类的，它就会可以在算法里面叫 O1 的时间，就是在常数的时间内把你找到它的位置在哪里。就像你比如说有一个 factor， 对，就比如说你有一个 array， 你要去一个索引，就每个都试一遍，
很快的。
对，哈希的话就直接就到了。
那如果我在这里 dot 一个不存在，这里面没有说明过，它就会报错，是吗？
对，报错。
感觉
是的。
所以 OK，那谢谢。
这个循环它推出的条件是什么？因为你不是 n 就会减一减二，
那 n 小于等于2的时候 f 等于，
但是这个没有，就是 else
啊，对，这个只有当 n 大于2的时候才会运行。这个 else 的意义就是 n 大于2。
哦，
对，它是那个 branch 的一个部分。
而且它那个输入这个是9和10的时候，为什么抗的一直是4？
一直是4，不会吧？
就是刚刚就是调了几下，然后抗的一直是4。
它应该是会变的，但是变得不像预想的那样，它应该是比如说，对，如果是9的话，至少应该要接近几十次才对。
刚上课举的那个例子
啊，
它是10的时候，
是10的时候，
然后那个抗的前4次都是4，然后第5次变成5。
对，这个是10的时候哈，然后就是大概是这个样子。10的时候大概是100多次，然后它是从什么时候开始呢？是从9开始的。对，因为它要先进入到最里面那一层，就是它要，比如说你是10的时候，它要先靠9，但9还不会 print， 9要先靠到8，8要靠到7， 7要靠到6， 6靠到5，这个时候 count 就在一直递增，增到最里面那一层 n 小于等于2的那一层，它会跳到第13行直接 print 出来。那一层的时候，它就相当于是9次，它从9次到了最里面那一层，然后 print 出来，然后它再跳到外面那一层，外面那一层的时候是10。
所以刚刚应该是14的时候前4次。
对，是4的时候应该前4次是，或者5的时候前4次是4，我试一下5的时候。对，5的时候第一次应该是4，因为你调用了4次才进去。对，跳出来，然后跳出来是5，然后就这样一步步往外跳。你要跟踪它的话，你要用那个 debug 的那些工具，你可以慢慢才能看出来。
前4次都是4，是当 debug 的时候。
啊，debug 的时候前4次是4是吗？哦，那个时候我还没 print， 是不是？是不是我还没 print 的时候？你看一眼啊，就这个对吧？把它断在这里哈。我让它往个4次，第3次它就跳出来，我用10吧，用10来试一下。这个时候对吧？你是说这几个都是4对吧？对，因为这个 count 是共享，所有每一次 call 它用的是同一个 count， 所以它是共享，但它还没有 print 出来，它没有 print 出来，它要是 print 的话，第一个应该是9才对。它还没 print， 它还在这一层呢。这一层的时候 n 等于7，我再让 n 等于7的时候，它会 call fib 6，这时候 n 等于6，它是说 count 变成了5，我再上 n 等于5 count 变成6，再往上，一直要到2。2的时候它已经跑出来了，因为我没有断点，没有打到那个位置，它就会直接打印出 fib 等于第一轮一输出就是9，就它会一直跑到最里面那一层 print 出来，然后再往外跳，每一次看的其实都已经增加了。对，
那个 unsigned 是什么意思？
unsigned 就是没有符号，就是它永远是正数。对0或者正数。对。
那个递归的话，它是不是进行那种多操作的比较抽象？我感觉就是
你
如果递归你只用它进行费多纳切式列的计算的话，它就会非常清楚。但是
这个清不清楚？这个情况，
这个我觉得并不清楚。你是把它放到那个 temp 之后，然后就再进行第2次操作，只要感觉操作一多起来，然后就会变得特别抽象。
对，是你思考过程变抽象。如果你思考过程很简单，好，我汉诺塔函数在做什么事情？就是把 n 个盘子从 start move 到 end 里面，对不对？我假设它能成功，我假设 n 减1个能成功，那么我就先把 n 减1个先从 start 放到中间放一下。这个时候我那边 start 那个位置剩下最后一个盘子，那个盘子我把它直接 move 到最右边，对不对？然后我再把剩下的 n 减1个从中间那个位置 move 到最右边。 对，就是如果你思考成这样子的话，你就不会觉得很抽象。如果你要把它一步一步想清楚，确实很抽象。
好，
是的，
谢谢。
嗯。